Hello everyone, I'm Jyun-Jie Liao, and today I'm going to talk about affine extractors for almost logarithmic entropy. And this is a joint work with Eshan Chattopadhyay and Jesse Goodman. So randomness is a very powerful resource in CS. It can be used in algorithm design, and it's also essentially required in cryptography. And most of these applications assume that we have access to perfect randomness, and here by perfect I mean a sequence of uniform and independent random bits. And actually it has been proved that having perfect randomness is necessary in some very basic cryptographic applications. But the randomness we obtain from nature is usually defective. So this means in order to use this randomness, we need a way to purify it first. And this motivates the study of randomness extractor. An extractor is a deterministic algorithm that converts a weak source into a uniform random string. And here by weak source I mean a distribution which contains some amount of randomness, and we'll formally capture it by the amount of randomness by its mean entropy. So we say a distribution X has mean entropy K if the probability of X outputting any fixed outcome is upper bounded by 2 to the minus K. And we say X is an NK source if it has n bit and mean entropy K. And you can think of an NK source as a uniform distribution over a set of size 2 to the K. So ideally our goal is to construct an extractor which works for every source that has high enough mean entropy. But it turns out that it's impossible to construct a deterministic extractor that works for every NK source, even if we require the entropy K to be very high. So this means if we want to get an extractor, then it's only possible to construct it for a specific class of sources. And here is a list of some very natural and well-studied class of sources in the literature, and we'll focus on Phi sources. And a Phi source is a uniform distribution over an affine subspace of dimension k over the vector space F2n. And a Phi source is interesting for several reasons. So first, it's a natural generalization of another well-studied class of sources called oblivious big-fixing sources. And in fact, the state-of-the-art extractors for oblivious big-fixing sources actually rely on this generalization. And second, a Phi source also naturally comes up in a cryptographic scenario where we have a uniform secret, but then a linear function of this secret is leaked to the adversary. And in this work, we want to construct an extractor which works for every NK affine source, and our goal is to make this entropy requirement K as small as possible. And we will focus on the case that we just want to output one bit which is close to uniform within the small constant error. And it turns out that if we require the entropy K to be small, then this is already very challenging. And we can use probabilistic method to show that an affine extractor exists for entropy K slightly greater than log n, but we don't know how to construct it, and we can't even guarantee that the existential result is efficient. And it turns out that log n is also the best possible bound we can hope for. And affine extractors for low entropy have some interesting applications. So first of all, based on some very non-trivial and interesting reductions, some researchers show that affine extractors also work for many other interesting class of sources. And it has also been proved that the best circular bound for general Boolean circuit we know so far is for affine extractors. And next I will briefly introduce some prior works on explicit constructions of affine extractors. So a folklore result shows that an inner product function is actually an affine extractor for entropy slightly greater than 0.5 n. And then Gabizan and Ross showed how to construct an affine extractor for any positive entropy, but his result only works for a large prime field, and but we really need the affine extractor to work for F2 for some applications such as circular bound. And then Borgen showed how to construct an affine extractors for over F2 for entropy slightly sublinear, and then Yehudayev and Lee obtained a similar result using a simpler construction. And then finally in 2016, Lee obtained the first affine extractors for polylog entropy, which is a very strong result. And the very natural next question to ask is, can we get an affine extractor for log entropy? And it's also interesting to compare affine extractors with the recent line of work on two-source extractors. So two-source extractor is an extractor that can work for two arbitrary independent weak sources. And in 2016, Chattopadhyay and Goodman constructed the first two-source extractor for polylog entropy, and then Li modified that construction to get an affine extractors for similar parameters. But for two-source extractors, there were a lot of subsequent work which eventually improved the entropy requirement for two-source extractors down to roughly log n times log n. So it is interesting to ask whether a similar improvement is possible for affine extractors. And in this paper, we give a positive answer to this question. We show that there exists an explicit extractor for nk affine sources where the entropy k is roughly log n times log n. And recall that the optimal bound is log n, so our result is actually very close to optimal. And next we'll give a brief discussion of our proof of our main theorem. So first we need to briefly recap the construction by Li, and then we'll see what's the main challenges for getting the entropy requirement down to almost logarithmic using the same constructions. Then we will see our solutions to these main challenges, which eventually give us an affine extractors for almost logarithmic entropy. So before we talk about Li's construction, first we need to introduce the Chattopadhyay argument framework for two-source extractors. So the CZ framework works in the following two steps. The first step is to convert the two independent weak sources into an intermediate model called Nlpf source. Then in the next step, we will use an extractor for Nlpf source to obtain uniform randomness. And an Nlpf source is a source that has d bits, and we know that some of the bits are good and the others are bad. And the good bits are guaranteed to be t-wise independent, where t-wise independent means if we look at any t bits, then they look uniform. And the bad bits can depend arbitrarily on the good bits. But it turns out that if the number of bad bits is small, and if the independence number of good bits t is large enough, then an explicit extractor exists. And for this work, you can think of t as a constant and the number of bad bits as d2 is 0.4. And next we will focus on the first step, which is converting the two independent sources into an Nlpf source. So a very crucial tool we need to use is called seeded extractors. So seeded extractor is also an extractor that tries to convert a weak source into a uniform random string. But the difference is it takes a second input, which is called the seed. And the seed is an integer range from 1 to d, and the guarantee we have is if we enumerate every possible seed and collect the output, then we are guaranteed that most of the outputs are good, which means they are close to uniform. And some of the output rows can be bad, but we are guaranteed that the fraction of bad rows is upper bounded by epsilon, although we don't know exactly which rows are bad. So if we can sample the output uniformly, then with high probability we'll get a uniform string. And after a long line of successful work, we now have very good seeded extractor, which has a range of seed being poly n over epsilon. And this is basically optimal. And next we are ready to show how to convert two independent sources into an Nlpf source. So in the first step, we will enumerate every possible seed for a seeded extractor and apply it on one of the source. Then we get this matrix in which most of them are good, which means close to uniform, and only some of them are bad. But the difference between this source and Nlpf source is the good rows can be arbitrarily correlated, while in an Nlpf source we require them to be t-wise independent. So the second step is to take the second independent source and apply a new object called correlation breakers to break the correlation between the good rows. And we will get t-wise independence for it, and this means we get an Nlpf source. So if we try to apply a similar construction for affine sources, then we will meet the following problems. So in the first step, we also apply a seeded extractors to get this matrix. But in the second step, we need an independent source to break the correlation. But in a Phi source setting, we don't really have this second independent source. So, but Lee observed that if in the first step we replace the seeded extractor with the linear seeded extractors, then although we don't have a second independent source, it turns out that the original affine source can be written as the sum of two distributions A and B, and the A part is guaranteed to be independent of B and the output matrix. So this means although we don't have a second independent source, we still have this independent part A implicitly hidden in X. So somehow we can still use X to break the correlation, but this requires a more general object called affine correlation breakers, which can handle this A plus B correlation. So Lee constructed both of these objects for polylog entropy, and this is how he got an affine extractors for polylog entropy. So if we are trying to get almost logarithmic entropy, then we will face the following challenges. So first, we need a linear seeded extractors with optimal seed range poly n over epsilon. But it turns out that previous construction with optimal seed range can only work for polylog entropy. And second, we need an affine correlation breakers which work for almost logarithmic entropy. And we actually know how to construct a correlation breaker in the standard independent source setting, which has entropy requirement almost logarithmic, but we don't know how to construct an affine variant before this work. And of course, because it can handle a more general case, so it's harder to construct than the standard ones. And next we will talk about our solution to the first problem, which is how to construct a new linear seeded extractors which satisfy the purpose of these applications. So the first observation is we only need a linear seeded extractors with the short output. So with this observation, we show the following lemma, which says if we just want the output length to be c times log n, where c is a function of n but is very small, then we can actually get an almost optimal linear seeded extractor which has seed range poly n times some slightly super polynomial in epsilon factor. And although the exponent in the 1 over epsilon term is super constant, but it's still very small. So in the second step, we can apply an error reduction trick by Ben Arroyo and Tashma to further get the seed range down to poly n over epsilon. And the drawback of this error reduction is we will only get a somewhere random linear seeded extractor, which means for every seed, we don't really get a uniform output, but we get some candidates of uniform output, and it's going to guarantee that one of the candidate output is uniform. But it turns out that this is sufficient for our application. And second, we will show how to construct affine correlation breakers. So the earlier construction of standard correlation breakers for polylog entropy use an idea called alternating extraction. So this is by alternating sequentially applying some seeded extractors, and Lee observed that this construction can be made affine by replacing every seeded extractor with a linear one. So by doing so, he got an affine correlation breaker for log square entropy. But it turns out that recent constructions which can work for almost logarithmic entropy are more complicated. And it requires a lot of subsequent work to get the entropy requirement down to log n times log n. And a natural idea is, although they are more complicated, they are still somehow based on seeded extractors. So maybe we can still replace every seeded extractor with a linear one. But the bottleneck here is we don't have optimal linear seeded extractors, so we can't just replace every seeded extractor with a linear one that has the same parameters. And because the use of seeded extractor in this recent construction is very complicated, so the choices of parameters will become very tricky, and it's not even clear that it will work without any loss of parameters. And even though it worked, like we still need to reprove the correctness, which doesn't sound very ideal. So in this work, we show a modular approach which can convert a standard correlation breaker to an affine correlation breaker, even if the standard correlation breaker construction is like more complicated than the original ones. So to do this, our first observation is recent construction of correlation breaker can be viewed as a two-party communication between a weak source X and a uniform string Y. So for Y, you can think of it as like one row from the matrix that we are trying to break correlation for. So the two-party communication work as follows. So initially, they shared a public transcript which is initially empty, and then in the first step, the X side applies some deterministic function on X and the transcript and get a new message R0, and then make it public. And then Y, now in the next step, Y can see this R0, and Y will use Y and the new message R0 to compute the new message S0 and send it. And the next step, X can see S0, and in the next step, Y can use R0, R1, and so on. So a very important property in this two-party communication view is condition on the at any step of the computation, condition on the transcript Z, we can guarantee that the two source X and Y are independent. It turns out that this is a very important property in the analysis. And when we are in the affine setting, we can no longer guarantee that X and Y are independent condition on the transcript because it's not true at the beginning anyway. So the new property we want to guarantee is condition on the transcript Z, the A part and the BY are independent. But this is not trivially true because what we have is a two-party communication between X and Y, but not between A and BY. So, but our idea is we observe that if we have the following properties of the function that we are applying on the both sides, then we can guarantee this. So the property we need is we need the function f on the x side to be linear and the function g on the y side to work properly for weak source. So what I mean by this, so if you consider g as a seeded extractor, then of course it works for weak sources. But in the actual construction of correlation breaker, this G can be something more complicated, like for example, like another correlation breaker, or can be like something called an independence preserving merger. So with these requirements, we get guidelines for our constructions. So first, we want to keep every function f on the x side to be as simple as possible so that we can make it linear. And in this work, the construction we use will simply just every time we apply a function on the x side, it will simply be a seeded extractor, so we can easily make it linear. And second is we want to make sure that every function g on the y side can work for weak sources. And it turns out that for most of the building blocks we use, such as flip-flop construction and independence preserving merger, they all satisfy this condition. And you can check our paper for more details. And finally, let me mention the subsequent work. So using the idea in this paper, in the subsequent work, we show how to get a black box reduction from affine correlation breaker to standard correlation breaker which preserves the parameters. And this immediately gives an improvement of the entropy requirement. And although the improvement is very slight, but the message here is if in the future we get any improvement for standard correlation breaker, then this directly gives an improvement for affine extractors. And finally, let me mention some open problems. So one interesting open problem is how do we get improved parameters for affine extractors, and then some interesting parameters that we will care about is how to get negligible error and how to get the output length down to linear in entropy K. And second thing is whether we can get simpler construction for affine extractors. And note that both of these questions will be interesting even if we just require the entropy K to be n to the 0.99. Thank you for your attention.